Hello everybody, my name is Shashank Agarwal and I would like to present here some of the work we have done at TU Delft. We have named this project OctoRay and this short video aims to explain more about it. The aim of this project is to build a framework to allow any data analytics task to be scaled across hundreds of FPGAs using Python. This is achieved using the principle of data parallelism, where we split up our input dataset into partitions and perform analysis on these simultaneously. This helps us in preventing over-provisioning of hardware resources, reduces the risk of system failure, and provides us the ability to easily scale up or scale down our cluster. So this is a schematic representation of the system. On the left, we see the input data on which we would like to perform some computation. Using Dask, which is a Python distributed data processing framework, we can partition this data and dispatch it to remote hosts or workers which are connected to FPGA boards. Dask will then collect the results and merge them to form the final output. This solution supports several FPGA cards attached to a server by running one Dask worker thread for each FPGA and can also scale to hundreds or thousands of servers. Most data analytics pipelines consist of two broad stages, data preparation and data analytics. The system described earlier can be used to accelerate both these stages. As a demonstration, we have picked data compression and machine learning, specifically neural networks, as examples for these stages. We show that both these stages can achieve significant speed up when using OctoRay. This is a video which shows how we used Python to scale data compression to two U50 FPGAs. The FPGAs were provisioned from the Nimbix cloud, and the FPGA kernel was built using Vitis libraries. On the left half, we see a Python notebook, which is responsible for coordinating the entire process. Here, we define the remote method which will be executed on the FPGA connected hosts. This method essentially calls underlying Python drivers to communicate with the FPGA. This next step is the control logic to read our input data, partition it, and distribute it to the FPGA hosts. We then wait for the results. The live execution of the tasks can be monitored on the task dashboard as shown on the right. After merging the results, we check the output for correctness using the gzip tool in Linux. This graph shows the end-to-end runtime for the compression task shown in the video. Using a cluster of two FPGAs to compress files of different sizes led to a 2x improvement when compared to using just one FPGA. As a baseline benchmark, this setup was also compared to purely software-based compression tools. A 2 FPGA cluster was found to have a 4 times higher compression throughput than a multi-threaded software compression tool. As an example, for the second stage of the data pipeline, we performed image classification using a quantized neural network built using Xilinx's FIN framework. For this, we used the much larger ZAC cluster. For different subsets of the CIFAR10 dataset, an 8 FPGA cluster was found to be 8 times as fast as a single FPGA. Also, this setup is faster than a software implementation of the same neural network running on a CPU. By representing our measurements in a plot between cluster size and system throughput, we can clearly see how the system scales with more FPGAs. Doubling the cluster size improves the total throughput by 2 times and so on. In other words, the performance of the system increases proportionately with the size of the FPGA cluster. To conclude, OctoRay lets us build multi-FPGA clusters which can outperform both single FPGAs and software implementations. We have shown that for both data compression and neural network inference, which are examples of the two primary stages of a data pipeline, the performance scales linearly with the cluster size. Also, our measurements show that for these two applications, a 2 FPGA cluster outperforms the corresponding software implementation by 4x and 12x respectively. Such a cluster has many notable properties. It can be built using various combinations of FPGA and host machines. It lets us use any FPGA kernel as long as it can be wrapped in a Python wrapper. Furthermore, these clusters have been tested to work with various hardware platforms such as Ping Z1, AWS F1, Nimbix, TU Delft's in-house FPGA servers, and also ETH's ZAC cluster. Here are links to our codebase and our Hackster project page. And we would like to thank Xilinx for the U50 FPGA loaner card and also for access to ETH's adaptive compute cluster.